I said, I work in the University of Aix-Marseille, and today I will introduce you to the linear response theory and the logarithmic function. So first of all, we should focus on this word, which is response. By response, we mean the response of a system to a perturbation. So, so I was saying that even if the perturbation is smaller, we can obtain some information on the system that is perturbed by this kind of perturbation. For example, the sound of a bell provides information on the elementary excitation, and the normal modes can be can be used to guess the structure or the composition of the bell. Or if we take an electronic system, this electronic system, if we perturb this electronic system with an electromagnetic radiation, with an elastic scattering of particles and so on, we can obtain some information on the electronic excitations, or, for example, normal modes or phonon modes. One example is the optical absorption spectroscopy. In this kind of experiment, there is an incident radiation which irradiates the sample. Then there is a part of this radiation is transmitted. From the transmitted radiation, we can have information on the absorption on the absorbed radiation, and from this kind of information, we can get, for example, the electronic band structure or single particle excitations. The point is now the question that we have to ask is the following, which is why we can obtain this kind of information by an experiment like that one that I showed you, the absorption spectroscopy. The answer is more or less on this slide, in the sense that when there is a wave that propagates inside the material, this wave is attenuated, because the radiation interacts with the material, and the material influences the propagation of the radiation. So if we have a look at, the solid line, this line represents the propagation of the radiation inside the material, which is attenuated, as I said before. This is because the electric field has this kind of form, let's say. There is at the exponent there is a complex quantity, which is the refractive index, and so for this reason we have a damped oscillation, and the refractive index is related to the electric constant, which is also a complex quantity. And so in the light absorption and transmission is related to this quantity. So the next step is to try to describe the interaction of light with the radiation with the material, and the influence of the material on the propagation of the wave or the radiation. And this is described by the Maxwell equation in the presence of matter, which are also graded on the foot of the statue in honor of James Clerk Maxwell in Edinburgh. In this kind of equation, we have the electric field, the magnetic field, but also the magnetic field strength and the displacement field. These two appears exactly because when the radiation propagates into the material, the electric field and the magnetic field are converted in these two quantities. And we have to we take into account the fact that the total charge which is given by the composition to two terms, the external charge plus like an induced charge. And these two quantities, the total charge and the external charge, are related to the electric field and to the displacement field by the Gauss law. From the materials equation, we have that the displacement field is equal to the total electric field plus the polarization. So this is the total electric field, and then when there are some dipoles and polarization charges which are created inside the material. In general, the polarization is a Taylor expansion of in terms of powers of the electric field. If we truncate this expansion at the first order, we have the so-called linear response theory. So here, and this quantity is called the response of the response function of the material to the perturbation. One thing that I forgot to say is that the response function, we have the information on the response of the material to the perturbation. The material, in a certain sense, absorbs this light, this energy, and converts energy into, for example, into electronic excitation. This is the linear response theory, and you see that chi in general depends on R and R prime. If the dependence goes like R minus R prime, we do the Fourier transform and we obtain the polarization in terms of the vector Q and the omega and the frequency omega. So we have chi times E, which this kind of relation from the materials equation is written like this, and the displacement field is epsilon times E, where epsilon is the electric function, which in general, so it's a complex quantity, and moreover, it can be a tensor. So that the electric field may be a different may have a different orientation with respect to the electric field. For an isotropic and homogeneous medium, the elements. So in this tensor, we have longitudinal the component, the longitudinal component, the transverse component of this electric function. And in general, for an homogeneous isotropic medium, the longitudinal and transverse components are independent response function, which do not mix each other. And the longitudinal the electric constant describes the response of the medium to a scalar potential, while the transverse component describes the response of the system to the electromagnetic radiation, or to the response to a medium to a vector potential A related to the electromagnetic radiations. Well, after some manipulation, we can obtain this kind of expression, which says that for Q going to 0, the two components are equal, in the sense that when the wavelength is very big, is very large, we cannot distinguish between the longitudinal and transverse components. What I'm telling you is contained in this book, which whose title is Electrodynamics of Solids, from Martin Dressel and Georg Brunels, that I used as a reference for this talk. So imagine that we want to obtain the response to a longitudinal field. So we start from the material equation written for the longitudinal components. We rewrite the polarization in this way, as we have seen in the previous slide. So the expression of chi is the following. And from the Gauss law, we obtain that the longitudinal The response to longitudinal field is written in this way. It's the ratio between the induced charge and the total charge, while the longitudinal component of epsilon is equal to 1 minus induced rho over the total charge. And 1 over epsilon, and the inverse of epsilon L is equal to this expression, 1 plus induced rho over external rho. So I want to, okay. I would like to go on with the practical example of calculation of the longitudinal response. In this case, we are considering a very simple Hamiltonian, which consists, which is given by H0 that I will describe plus V. H0 is the Hamiltonian of an electron in unperturbed periodic potential, while V is the interaction energy with the local electromagnetic potential. So we treat this problem by introducing by using the reformulation of Schrödinger equation, which is written here in terms of one particle density matrix, and where rho is the density matrix. This density is decomposed in two terms. One is the unperturbed density, and the other is the induced density. So we have H0, for H0, we have as eigenstates, I will have the eigenstates as KL, vector K and bound L. Epsilon KL is the eigenvalue, the corresponding eigenvalue, and the KL, the state KL is a block function, where UKL is a periodic function. This KL is eigenstate of H0, but also of the density matrix rho 0. Well, the density is expressed in terms of density matrix in this way. By the trace of the density matrix rho 0 times the delta function. So if we go on and we expand the equation, we expand this equation by replacing H0 and V, we obtain this kind of equation with 4 commutators, but we neglect the fourth because it's a second order, because it's at the second order, so we neglect it. And we what we would like to obtain is a relation between the induced density and the induced potential, because as I showed you before, in the expression of the electric function, we have 1 minus induced rho over total rho. So we want to find this kind of relation between the induced rho, the induced potential, and then which has of course influence the total potential and so on. So we relate this the induced charge density to the total potential V, which contains the external potential and the screening potential. And the induced potential is related to the induced charge via the Poisson equation. So, as I said before, we have neglected this commutator, and we end up with 3 commutators. The first one, and then the first one is 0. And then we project on state K and KL and K plus QL prime, and we obtain so for this commutator, which is underlined in green, we obtain the difference of energies times this matrix element, plus for this one, which is underlined in red, we obtain this expression, which is written in terms of the difference of the Fermi function that now I realize that I forgot to say. so the states, the block states that I use KL are also eigenstates of the density matrix with S0, the Fermi distribution function as eigenvalues, times this matrix element. So now we expand the total potential in the Fourier components, and we obtain this kind of expansion here. Now, you see this term is an integral over the entire medium, and we can rewrite this integral over the entire medium as an integral of the unit cell, and plus an additional summation over all the other unit cells, and thanks to the periodicity of the UKL. In doing this, we use this result to obtain an expression for the dielectric function. We will obtain in a few moments. First of all, we use the so-called adiabatic approximation. We say that the external potential is turned on gradually at t equal to minus infinity, and then the time dependence is given by exponential eta t, and the same behavior is assumed for the total potential, induced potential, and induced density. So once this assumption has been done, and with the Fourier transform, we obtain that for the matrix element of rho between these states, we obtain, and then we have to send the eta to 0. So we have the limit of eta which goes to 0, the difference of the Fermi occupations, and divided by the difference of energies times this potential and this matrix element here. I want to stress the fact that we are searching for a relation between the induced rho and the total potential. But we have a relation between, but we have to start from consider the fact that the total potential is the external plus the induced one, and the total is the external divided by the electric constant. And if we combine the two, we obtain that for the total potential, we obtain the induced potential divided by 1 minus epsilon. This is useful because this kind of relation is important to establish the relationship between the induced potential and the induced rho. And finally, the Nabla square of the induced potential is related to the induced density by the Poisson equation. And putting everything together, okay, we have this kind of relation here, the induced potential in terms of the total potential, and finally, since we have established this kind of relation, we can obtain the electric function. And the electric function that we obtain is the following, which is the Lindau formula for the electric function for the longitudinal response. And I want to stress the fact that this quantity here resonates at the differences in energies. And of course, this is a complex. We can extract the real and imaginary part, and in particular, for example, the imaginary part gives information on the optical absorption that are here. Let's say that this denominator describes this kind of single particle electronic transitions from band L to band L prime. The same information are contained in the chi, which is which is here. So the poles of chi are centered at energy differences. So in this case, we are in the independent particle approximation. We are considering these single particle excitations. And this kind of, so the demonstration that I gave you for the independent particle expression of the electric function is contained in this book, but is also the subject of this paper here, the Heinrich and Cohen, self-consistent field approach to the many electron problem. And then I move the step forward and I had a look at this paper from Stefan Adler, which starts from the consideration that the previous paper that I cited, and which contains the derivation of the Wieland expression for the epsilon. So he claims that in that paper, Heinrich and Cohen do not include additional effects of interest in solids. So what are these additional effects? These additional effects are the non-local fields. And then he makes another consideration, the fact that in reality the electric constant is a tensor, so a purely transverse or a purely longitudinal can induces both transverse and longitudinal responses. And this kind of coupling does not appear in the isotropic free electron gas, because as we saw before, in the isotropic homogeneous material, the two responses are decoupled. While this kind of interaction is present even for cubic symmetry and vanishes only for propagation along special direction of a high symmetry. So starting, so we will stay on the right of this slide for a couple of slides, and then we move back to the local fields effects, because I just want to tell you what Stefan Adler tells in this paper. Actually, you see it starts with again from this time-dependent evolution of the density matrix with an Hamiltonian, which is the following. There is a potential decoupling with the potential vector and a scalar potential. And UR is the periodic lattice potential. And by assuming that the dependence of A and phi is the following, he obtains the longitudinal response, longitudinal component of epsilon, which was already demonstrated by Heinrich and Cohen in their paper, and that is that one we have seen before, the Wieland formula of the electric function. And then he calculates also the other components, the off-diagonal components, and claiming that they vanish if the electric function is assured to be isotropic. I think that is not in general true for crystal lower symmetry. But then now we move to the left part of the slides, and we have a look at how to interpret these local fields effects according to this paper. So he starts from an hypothesis of a cubic symmetry, a system of cubic symmetry, and if we suppose that there is a slowly varying external potential, which has this form, which is essentially constant over a unit cell. So this is the starting assumption. Then the local field effects actually enters because the macroscopic potential, which is an average over the material over a distance which is larger than the cell but smaller than the material itself, is different from the microscopic field, which instead can oscillate rapidly inside the unit cell. And this is expressed by the fact that the induced and the total potential have components Q plus G. This kind of okay, if we compare what I say here and what we had on the right of the slide, we see that in this case, here the rapidly varying oscillation have been neglected. In the sense that there is no difference between this macroscopic and microscopic potential. Following a similar derivation as we have seen before, we can have an expression of the induced potential in terms of the total potential, and then the final expression for epsilon, which is the following, which is a matrix in GG prime. Now, the fact that this is the matrix in GG prime comes also from the fact that we are including the local field effects, which takes into account the homogeneity of the system. The homogeneity of the system means that in general, the response function depends on R and R prime, and not on only on the difference between R and R prime. So for this reason, we have this kind of dependence in terms of G and G prime. Well, and now, okay, I will show you another approach, but this is quite similar, which is detailed in this paper. Now we start from no, we have three approximations, but we will focus just on the first two. It's the aim of this part of the talk is to show you if you start with a Kohn-Sham Hamiltonian, what does it mean in practice when you calculate the independent particle response of your system, or the independent particle plus the local field. The difference comes from the fact that you start from two different Hamiltonians. In the first one, the density is considered to be rho zero. It means that it doesn't vary. It stays at the equilibrium condition, while in the second case, we allow the arc potential to depend on rho, which can vary and can be different with respect to rho zero. So in the first case, we have this Hamiltonian, the single particle energies are the eigenstates, eigenvalues are the over H0 are labeled by N. The notation is a little bit different with respect to my previous slides, where I had K and L instead of N. And then we have so these the N are the block functions, as we have seen before. So okay, the approach is very similar to what I presented to you previously. We have to start from the density matrix, which is expanded in this basis, in the basis of phi, the block states against the Hamiltonian H0. And the density rho zero is the average of the density matrix, which is square modulus of phi n times the occupations, which can be 0 or 1 for semiconductor insulators or Fermi distribution for metals. So we apply the total potential, and we write the equation for the evolution of the density matrix, expanded in the base of in the block states against state of H0. And then for the response function, we calculate the derivative of rho with respect to this total potential. And the demonstration goes, is very similar to what I've shown you before. So we have these two commutators. One is neglected because it's of the second order, as we have seen. And the first one gives the difference, the energy difference. The first one, the commutator H0 rho, gives the energy difference, while the second one gives the difference between the occupation factors. And by computing this derivative, and we obtain on the left the derivative with respect to time of the response function, the energy difference, the difference between these occupation factors, and if we transform, we obtain the K0, which has the same expression as I showed you before, which is the same expression we have seen before for the Lindland expression of the epsilon and chi. At the denominator, we have the poles of these K0 are centered at the energy differences, and at the numerator, we have the differences of the occupations, which this occupation factor selects transition from valence to conduction bands. So with this expression, we obtain the epsilon, the electric function, which is in this case just it is the expression of epsilon, the electric function in terms of at an independent particle level. It means that we are just describing single particle excitations without including local field. And we have this red line, the red line is the experiment, the black line is the independent particle without local field for silicon. This is the typical absorption spectrum of silicon. And we see that the agreement is not good, but we can say that maybe it's the starting point. It's the Hamiltonian, which describes the electronic system that is not correct. Let's say it's not adapted. So for this reason, we move step forward. We consider the possibility that the Hamiltonian, the dependence of the density may vary, but just with the electric potential. And by doing this, we are proceeding with the same way. We obtain an expression for chi, which is a matrix. It's a Dyson equation for chi that can be inverted, and then with this we can calculate the electric function. But in this case, by letting the density vary in the electric potential, we are including the non-local field effects. So we are doing independent particle approximation with the local field effects. And so we have this, again, the solid line, the dotted line is the experiment. The green dashed line is without a local field effect. With local field effect, we have a slightly different spectrum, but it's not enough. It's not enough, so maybe we should go on. Going on means assuming that the electronic transition from valence to conduction band are not independent, and maybe we have to consider the excitomic effects, which means using as a starting point the third Hamiltonian that I have in my previous slide, where not only the electric potential but also the exchange correlation potential. We have an Hamiltonian where the density is allowed to vary not only in the electric potential but also in the exchange correlation potential. But this is go beyond the aim of my talk. So just yes, in order to approach the conclusion, pay attention that when we are so we have this from the experiment, we have access to from an optical absorption experiment. We have access to the imaginary part of the electric function that we call the macroscopic electric function. From the theory, we have a relation between the total potential and the external potential, which is expressed in terms of the inverse of the electric function, which is a matrix G and G prime. In order to be able to compare the calculation with the experiment, here we have to perform a spatial average over on a length which is larger than the unit cell. Now we have to do the spatial average, which consists in taking just the G equal to 0 and the G prime equal to 0 components. But in order to connect the electric, the macroscopic electric function and this quantity, we have to invert. We have to calculate 1 over this quantity, and the tricky point is that when you have a matrix, and you have imagine that you have a matrix in terms of G prime, you have to invert this matrix. All the elements of the matrix count for the calculation of only one element of the inverse one. So the matrix is completely calculated. We calculate the entire matrix, and then we invert, and we get just the G equal to 0 and G prime equal to 0 because they correspond to the spatial average of this quantity, starting quantity. And in the case of absence of a local field, this macroscopic electric function is essentially given by the epsilon, the electric function, which has already G equal to 0, G prime equal to 0. Yes. Oh, okay. I don't know if I have time, but I just wanted to show the case of the electronic screening in 2D systems, which is published in this paper. And they show that if the three-dimensional static microscopic dielectric constant is used, then you can imagine that we have a 2D system. In the case, the spacing between the layers goes to infinity. And we use the three-dimensional static microscopic dielectric constant. This quantity goes to 1 for every Q point in the limit of large separation between the layers. And actually, they let's say proposed an expression for the two-dimensional macroscopic electric function, which allows to recover this kind of behavior here, the black line, and while for larger spacing we recover this this line, which tends to the okay, this was MOS2. In the case of L equal to the separation between the layers is equal to 6.15 angstrom in the bulk. We obtain the value for the bulk. And with this, I conclude, which are the take-home messages. Okay, the linear response, the first order response function to the external field. The choice of the Hamiltonian set approximation for the response function, and the dielectric function can be calculated summing over the valence and conduction transitions. Sometimes an independent particle approximation is not enough to reproduce the experiments. and the inclusion of local field effects take into account the homogeneity of the system. That message, and okay, this just works with this kind of topic is quite vast. There are discovered in plenty of books. For this presentation, this time I decided to use this one, but it's up to you to search for yours. And thank you for your attention.